All right, our next topic is the Reynolds transport theorem. And what the Reynolds transport theorem, or I like to abbreviate RTT, what it does for us is allows us to take our normal system laws that we use for a particle or we could use for a whole closed system and convert that into control volume equations. Control volumes are different because our control volume sits there while particles come in and out, so we have to deal with inlets and exits. Whereas a closed system or a particle in physics, that's that Lagrangian point of view, we can just directly use F equal ma and so forth. So things are a little bit different, and this helps us switch from our system laws to our control volume laws. Now, don't freak out. Has a kind of a scary name, Reynolds transport theorem. Ooh, yeah, but it's easy to use. So we'll figure out how to use it here in the next page, and you'll be able to use it and create all kinds of control volume, general laws for control volume. So that's pretty exciting. First thing you got to do is take your system laws, conservation of mass, conservation of momentum, conservation of energy, and convert them into something with a derivative. So starting with conservation of mass, if we look at our closed system, well, mass equals constant. Nothing can come in or go out, or the same thing for Lagrangian physics kind of scenario. So if m equals constant, if we want to get this in the form of derivative, well, that means dm dt equals 0, right? dm dt. We want our derivatives all be with respect to time or rates. So this is what we're going to use when we use the Reynolds transport theorem. Conservation of linear momentum, in other words, Newton's second law. Sum of the forces equals ma. Well, we want a derivative, so let's convert ma into dv dt. And now we want just a derivative, so let's pull that m inside our derivative. We can do that because m is a constant. And this is what we get. Sum of the forces equals dmv dt. That's mv, see that? That's momentum. That's why it's called conservation of linear momentum. If we do angular momentum, h is the angular momentum, so we just get the sum of the moments equal dh dt. We're not going to really deal with that in this class. You'll learn more about that in dynamics. And then conservation of energy, we saw that in thermo. We'll have a different form of it in fluids, but as a rate, we're going to have that q dot minus w dot equals, and we'll just call it dE dt. Now that E contains your internal energy, kinetic energy, and potential energy terms. Okay, but that's what we'll use. All right, so let's move on and see how do we use this Reynolds transport theorem. What exactly is this transport theorem? Okay, again, what it's used for is to convert those laws that we just saw above into control volume laws, because they were for the particle in physics or a closed system. Okay, so this is it. This is Reynolds transport theorem, and again, it looks pretty scary because it's got all kinds of integrals and derivatives both in it, but it's really not all that bad. So basically, you take your system law and you look at it, and it's going to be some form dB dt, where B is, depends on the system. If it's conservation of mass, B is just m. Okay? And then what you have on the right-hand side, so the change in whatever B is inside the system has to be what's changing inside the system plus what's going in or out of the system. So this is what's changing inside the system. So basically, over that whole volume, what's changing. And then this is what's going on at your inlets and exits. Okay, so beta, all beta is your specific B. So you figure out what B is, and then you divide by m to get your beta. Okay, so and again, x is the rate of change of this property B, and we're going to decide what that property is here in a second. And then the rate of change B inside. So basically, if more mass comes in than leaves, you're going to get an increase of mass inside. So you would have an increase of mass, and that would be contained in this first term, y. What's coming in and out is contained in that term, z. Okay? So using the Reynolds transport theorem, first thing to do is figure out what B is from your system law. And all it is is what's in the numerator in your d dt term, okay? So for conservation of mass, we're going to see in a minute, your big B is just m, okay? The next thing is to divide B by m to get beta. And the left-hand side then of your final control volume equation is the non-derivative part of the system law. So we're going to see again in a minute, if we look at the non-derivative side of conservation of mass, well, that's just zero. Okay, that's what I mean by the non-derivative side. Conservation of momentum, that would be sum of the forces. Okay, so we're going to write it as whatever that non-derivative is, and then equals this whole thing where we're plugging in betas. All right, so for conservation of mass, we're going to come up right now with the generalized equation for control volumes for conservation of mass. And what I mean by generalized is you have some arbitrary control volume, can look like anything, you got flow going every which way through this, and it could be changing in time as well. So that scribble means that there's no specific inlets or exits, flow is just going through it. So if you have some just arbitrary control volume, and flow is going through it in every which way. Okay, very arbitrary. Usually we won't have that situation. We'll be able to simplify this. Okay, so step one, figure out what B is. From your system law, you look at the ddt term, and for conservation of mass, our system law was dm dt equals 0. So B has to be m. Now to get beta, you just divide by m. So m over m is 1. So beta is just 1. Very simple. Okay, so our final control volume law for conservation of mass is left-hand side of control volume equation is the non-derivative part of the system law. Non-derivative part, well, that's 0 for conservation of mass. So 0 equals, and then we have our y part, what's going on inside. So we aren't going to write the ddt part. We just use that to figure out what B is. So it's 0 equals the y here. So ddt, the triple integral, because that's over the whole control volume. Beta is just 1, so we can leave that off. Rho dv. That v should be volume. All right. Plus our integral over our inlets and exits. Beta is 1, so rho v dot n dA. All right. So do you recognize that rho v dot n dA? You should, because it was your conservation of mass from the last video. All right, so at this point, you can stop and do quiz question 4 on Reynolds transport theorem. I do want to point out, though, that I threw a lie in here, and I meant to talk about it, but I didn't talk about it. So there is a lie, and it is actually in the first video, or set of notes. It's in the notes, but I didn't actually say anything about it, so it's a little tricky. So I want to point out that it was in that first video set of notes. So before the Reynolds transport theorem, if you look through your notes carefully, you might find that lie.